Hello and welcome to today's presentation, Practical Considerations for Conducting Perforation Inflow Tests. As promised on the presentation abstract, I'm going to discuss the suitability of this type of test for low permeability formations as an alternative to mini-frac tests. I'm also going to look at some advantages and disadvantages to running this test in comparison to mini-frac tests. So what is PITA? PITA is an acronym that stands for Perforation Inflow Test Analysis. The perforation inflow test is a type of a well test where the well is perforated underbalanced and is allowed to flow into a closed well bore. There is no production to surface, there is no metering of rates. The resulting pressure buildup is measured and analyzed. The data set that we get out of this test looks like a buildup test, except there is no production prior to the test. Provided reservoir-dominated flow was reached during the test, the analysis provides initial reservoir pressure, permeability, and skin. The well can also be perforated overbalanced, and the resulting fall-off can be measured and analyzed. This methodology works both ways for perforating overbalanced and underbalanced. Some background and history of this methodology. This methodology is not exactly new. It existed for some time before. Previously, it's also known as slug tests or closed chamber tests or PID, which is perforation inflow diagnostic, and some of you may have heard of this. Prior to application of these methods in the petroleum industry, starting about 1970, they were extensively used in the hydrology industry for years and years. So approximately 15 years ago, interest in tight gas reservoirs began to pick up, and conventional flow and buildup testing techniques began to show some shortcomings, such as impractically long buildup times due to very low permeability, large error bar on pressure extrapolation, since the final buildup pressure at the end of the test would not be close to the average reservoir pressure. Also, a lot of these wells were fracture stimulated. And we know that if we have a form of fracture flow, unique estimates of permeability and average reservoir pressure will not be possible. So PITA gained popularity as a test for tight gas wells that would be conducted prior to the fracture stimulation to obtain initial reservoir pressure, skin, and permeability. And between 2005 and 2010 or so, we have analyzed hundreds and hundreds of these tests. And by we, I mean the well test analysis group at PITA Associates, which is now part of a larger company called IHS. Over time, resource development shifted to even lower permeability reservoirs, and PITA tests were not performing as good. Mini-frac tests were more successful in very low permeability reservoirs, and I'm going to come back to this and explain this in a little bit more detail in a few moments. To put things into perspective, I'm going to quickly go over a sequence of operations for a typical PITA test. Run in hole and perforate the formation. Do not monitor the buildup, pull the guns out of hole. We need to run pressure recorders as soon as possible to start monitoring the pressure buildup or fall off. Run a wireline retrievable bridge plug complete with pressure recorders suspended below. Set the plug as close to the perforations as possible. This is an optional step, although it's always recommended, as it reduces the wellbore volume, which in turn reduces the wellbore storage effects. Alternatively, the buildup can be monitored at surface, and if there's a liquid level present in the wellbore, intermittent fluid levels should be taken. Leave the well standing as per the test design, and finally pull the bridge plug with recorders out of hole on the final day. So the procedure is fairly simple. Perforate the formation and monitor the pressure response. This is what a data set looks like. So what we can see here is just a build-up trend. The first step before we get into analysis is calculating the inflow rates. And this is done more out of curiosity than anything else. It's not required for the analysis, it's just shown here for us to see what the afterflow rates were. So now we get into the analysis. Just like in conventional well testing, a derivative is generated and plotted. This is an impulse derivative, and we can use this to identify and diagnose flow regimes. So we can see that early time data falls on a straight line with a slope of +2. The early time data in this example is dominated by wellbore storage. So this is what I'm referring to. In the late time, pressure data begins to exhibit horizontal trend, which is characteristic of radial flow. If radial flow develops within the time constraints of the test, unique estimates of permeability, skin, and reservoir pressure will be possible. However, this type of a pressure signature is more of an exception rather than the rule. Typically, we see data sets that are cut off as early as here, and in this case, we cannot determine even a range of characteristics because the data is dominated by wellbore storage. Sometimes the tests are terminated as the data begins to transition into radial flow. In that case, if we can determine a range of reservoir characteristics. This is just a brief review of what I just discussed. So we calculate and plot the pressure derivative. If radial flow develops within the test, unique interpretation is possible. Otherwise, hopefully a range of parameters can be determined. This is an example of a more typical data set. We see that the pressure data does not even begin to transition into radial flow. And in this case, we will not be able to determine even a range of characteristics. We will be able to determine the minimum permeability and the minimum reservoir pressure, but we won't be able to put higher bounds on these parameters. And this is not a data set we want to see. So how can we avoid this? Tests should always be designed so that reservoir-dominated flow occurs as quickly as possible. Looking at the equations, we can see that the variables that affect the pressure buildup are as follows. Flow capacity or permeability thickness. This is something that we do not have control over. However, it's obvious that the higher the permeability, the quicker the buildup is going to take place. Skin. Positive skin acts as a barrier to the propagation of the pressure transients. So in the presence of positive skin, the buildup is going to be significantly slower. Wellbore volume. Wellbore volume is always an issue that comes up when we talk about PITAs and mini-fracs and flow and buildup tests. And it's more of an issue in tight permeability formations and in gas reservoirs. So wellbore volume is essentially a big pressure cushion that is going to attenuate the pressure response of the reservoir. We're trying to test a low permeability formation while in direct communication with this pressure cushion. As long as the pressure in the wellbore is somewhat different than the pressure in the reservoir, this wellbore volume is going to mask the pressure response of the reservoir, and the pressure response that we're going to see is going to be that of a closed system, which is also known as storage effects, and it's important to minimize the wellbore volume as much as possible. Cushion pressure. Cushion pressure is the pressure in the wellbore prior to perforating. So it can be higher than the average reservoir pressure. In the case of overbalanced perforation, it can be lower than the reservoir pressure, as in perforating underbalanced. So the smaller the difference between the cushion pressure and the average reservoir pressure, the quicker the buildup is going to be, and less of an effect wellbore volume is going to have on the pressure response. Let's look at some of these items in greater detail. Wellbore volume. Time to radial flow is proportional to wellbore volume. Reducing wellbore volume by a factor of 100 reduces time to radial flow by a factor of 100. When time factor is important, the duration of the test can be reduced by setting a bridge plug above the perforations, which is what we always recommend. Depending on the wellbore configuration, the wellbore volume can be reduced even further by setting a bridge plug below the perforations prior to the test. PITA is not recommended in horizontal wells simply because of the large wellbore volume, and running plugs in the horizontal section of the wellbore is not practical. Also, instead of setting a plug above the perforations, what has been done in the past is it's possible to run a tubing string with a packer, and that tubing string should have a plug with recorders below it that's been pre-pressure tested. Of all the parameters that influence time to radial flow, the one that operator has control over is wellbore volume. That's the big test design item. So this is some synthetic data to demonstrate the effect of wellbore volume. This was generated for permeability of half a microdarcy and a skin of +2. So we can see here where the data begins a horizontal trend, that's when we can terminate the test. So reducing the wellbore volume from 40 to 2.4 meters cubed reduces the time to reach radial flow from 300 days to about 30 days to just a few days. More test design considerations. Skin and cushion pressure. Positive skin slows down the buildup. It goes without saying, but perforations must be good and effective for pressure communication with the reservoir. The less of a positive skin we have around the wellbore, the higher the chances of a successful PITA test. If cushion pressure is high in an underbalanced scenario, wellbore storage will have less of an effect. So theoretically, we want to minimize the difference between the cushion pressure and the reservoir pressure to minimize the effect of the wellbore storage. However, the underbalance has to be high enough to see an indication that we are in communication with the reservoir. The recommended underbalance or overbalance is about 500 to 1000 psi. Sometimes what can happen if the underbalance is too small and we perforate and we do not see a pressure response, and there is no way to tell whether that's due to poor gun performance or whether that's because the cushion pressure is so close to the average reservoir pressure. Effect of cushion pressure is minimal compared to skin as a factor that determines time to radial flow, and it just does not deserve that much attention in test design. So now we're going to compare the PITA and the mini-frac. I mentioned previously that mini-frac became a lot more popular than PITA test for very, very, very low permeability formations. And the main reason for that is that in the presence of positive skin and poor communication with the reservoir, time to reach reservoir dominated flow with the PITA test can be impractically long. With a mini-frac, we know we are seeing past the damage near wellbore region, and reservoir-dominated flow develops quicker in most cases. However, there's also a lot of unsuccessful mini-frac tests. In a mini-frac test, before we see radial flow, we need to go through the linear flow, and the time to radial flow in a mini-frac test depends on the size of the fracture generated, which is a function of the amount of fluid injected. And sometimes it's difficult to control, sometimes it's difficult to minimize the volume of fluid injected from a practical standpoint. After observing the breakdown, it's desirable to inject as little fluid as possible, preferably under 15 or 20 barrels. And sometimes it can be tricky from a practical point of view. However, if we take a PITA scenario with a little bit of positive skin on the wellbore, and we take a mini-frac scenario for the same formation, same properties, and we add a small frac in the mini-frac scenario, we're still going to see radial flow develop quicker than in the PITA scenario. Another drawback of PITA in very low permeability formations is sometimes it can be negatively impacted by supercharged pressure, that as wells, if wells are drilled over balance, there's a possibility that a supercharged region is created around the wellbore. And that's, again, like, that's not always the case, it's not always the rule, but we have seen that before. And if we're conducting a PITA, we can be testing within that high pressure zone, and PITA can point to an artificially high pressure. With a mini-frac, the thinking is that we break past that high pressure region and we're seeing more of a representative formation pressure. However, we have seen both PITA and mini-fracs being affected by the supercharged condition. And the way we can see that is if we have a flow and build-up test performed right after this PITA or the mini-frac test, and we have seen a couple of instances of both being affected by overpressure. Choosing between PITA and a mini-frac. PITA can be difficult to execute properly in tight formations, permeability less than 1 microdarcy, and that's due to long times for radial flow to develop. However, in a few moments I'm going to show you an example where the test was executed perfectly in nanodarcy rock. The choice comes down to which test is more convenient and operator preference. If somebody had success using PITA, they're more likely to continue using PITA. And PITA does not require fracking, and maybe the choice of fracking is not an option, such as if fracking is not allowed. PITA is not necessarily cheaper than a mini-frac, because during a mini-frac pumping is only a little bit of pumping is required, and PITA is not recommended for horizontal wells just due to the wellbore volume. Some other considerations. If wellbore configuration allows, pressure response should be monitored at surface with intermittent fluid levels. Wellhead pressures can be quickly converted to bottom hole pressures, and depending on the pressure signature, the test can be terminated early or extended. So this is test monitoring in real time. However, it's not always possible because the recorders are suspended below a plug, a downhole plug. PITA may be particularly useful for evaluating multiple layers, and so can be mini-frac. So perforate the lowest zone, run plug with recorders, move up hole, perforate the next zone, run plug with recorders, and continue doing this to test all zones. Let us look at the two examples that I have prepared. Example 1 is a shallow gas well with permeability of 0.5 millidarcy. What's interesting about this example is that a PITA test was followed by a flow and build-up test, and the results of the two tests were found to be in close agreement. It's not very often that we see a situation like this where a PITA test is followed by a flow and build-up test. So in this case, the results were found to be in close agreement, and the flow and build-up was used to verify the results of the PITA. The second example is a shale gas well where a PITA was successfully performed, and the permeability is 100 nanodarcies. Although the test was cut short by wellbore issues after 7 days instead of the planned 14 days, we were still able to get a meaningful interpretation because the test was designed and executed properly. Okay, let's switch into the software and look at example number 1. Now we are looking at the IHS well test software file for the PITA test for the shallow gas well example. So the raw data has been preloaded and the properties have been pre-populated. So let's proceed with the analysis. The thing to note here is that wellbore volume is calculated based on the actual wellbore configuration, and it's entered as an input here. So the inflow rates are calculated and shown. Then we can generate the pressure derivative. Looking at the late time pressure derivative, we can see that a horizontal trend is emerging, and diagnostic analysis of that horizontal trend gives us permeability to gas of about 0.33 millidarcy and a P star of 2378 kPa. Now let's proceed to modeling to verify these numbers. So we're looking at an analytical model. We have observed pressure data and we have calculated pressure data by the model. We can adjust the input parameters until we obtain a good match with the model, or we can get the computer to do that for us. So we're just selecting the parameters that we want to do automatic regression on. Then we want to double check the data. I recall seeing some issues with the late time data, so we're going to deselect points in the late time. Also, we're going to deselect the early time data because I know we won't be able to get a match to it, and we're not interested as much in the early time data as we are interested in the late time data. I'm going to add some weighting to the pressure data that's of particular interest, and we're going to see what result we get. So we're getting a permeability of 0.49 millidarcy and initial reservoir pressure of 2370 kPa, and the match is fairly acceptable. The reason that we're getting a higher permeability than we saw on the diagnostic analysis is because the straight line analysis assumes a flow regime is fully developed, whereas with modeling, we're acknowledging the fact the model accounts for the fact that pressure data at this point is still dominated a little bit by wellbore storage and is transitioning into radial flow. So the transition between flow regimes is taken into account, and parameters obtained from modeling supersede the parameters obtained from straight line analysis. So now let's look at the flow and build-up test that was carried right after. We are now looking at the well test file for the flow and build-up test that was done right after the PITA test. So the data once again has been pre-loaded, and let's proceed with the analysis. Appears that we're seeing a horizontal trend in the late time. Diagnostic analysis of this apparent radial flow gives us permeability to gas of 0.49 millidarcy and the initial reservoir and P star of 2390. Now let's do a quick model to confirm these reservoir characteristics. So I'm just going to add a little bit of weighting to the late time data and use the auto match feature once again. So we're getting a permeability to gas of 0.47 millidarcy and initial reservoir pressure of 2390 kPa. So we can see that the results of both tests are in good agreement with each other, which raises the confidence in the PITA solution. Let us now look at the second example, the shale gas with 100 nanodarcy permeability rock. PITA was performed to obtain an initial reservoir pressure and permeability instead of a minifrac test. To minimize the wellbore volume, a bridge plug was set below the perforations. Then the mini formation was perforated under a full water column with casing guns, after which a packer assembly was plugged in place and pressure recorders in the tailpipe was set above the perforations, and the thinking was to reduce the wellbore volume as much as possible. The test was cut short by a leaking bridge plug. Well, this was determined after the recorders were recovered and downloaded after the 14 days of buildup. The data was transitioning into radial flow after 7 days, just at the time that the leak in the plug developed, and we were still able to get a meaningful interpretation of the results. And that's because the test was planned and carried out properly. When the plug with recorders was about to be retrieved, when the operations on the well resumed at the end of the build-up test, there was no pressure at the wellhead, and this is a slightly overpressured formation, so there, if the top plug was leaking, we would see some pressure at the wellhead. So that's what led us to believe that it's the bottom plug that was leaking. Let's switch to this software and look at this example. We are now looking at the IHS well test file for the second example. The data has been preloaded, so let's jump right into the analysis. So the wellbore volume has been determined from the wellbore configuration, 0.36 meters cubed. Looks like the late time data is exhibiting a horizontal trend. Of course, we have to ignore all the pressure data that's affected by the pressure loss. Diagnostic analysis of the radial flow regime gives us permeability to gas of 80 nanodarcies. Now let's do a few models to determine the range of permeability. First thing we want to do is filter the data a little bit so the models run quicker. Then what we want to do is deselect the pressure points that are affected by the pressure loss. So it's about here that the pressure data is beginning to be affected by the pressure loss. And the easiest way to do this is just to look at the pressure derivative and say that all the points as the derivative begins to drop off are affected by this pressure loss. And finally, we want to add a little bit of weight to the late time pressure data. No. It's just like this. So I'm not going to say that permeability is auto match parameter. I'm going to vary that manually because we want to establish the minimum and the maximum. So let's see if we can get a match with 80 nanodarcy. Eighty nanodarcy should be the minimum permeability, although the match is not great because we're coming in a little bit higher here. So let's bump up the permeability to 100 nanodarcy, 100 nanodarcies. We can probably say that this is an acceptable match, and this is the low end of the permeability range. Let's copy this to another model and keep bumping up permeability until we determine the high end of permeability. So let's go to 140. And once again, we need to deselect all this pressure data, add some weight to these pressure points. Let's see if we can get a match with 140. Looks like we can get a fairly acceptable match. Let's see if we can bump this up to 160 and still maintain the match. It looks like we're beginning to lose the match and the curvature, and we can actually see that the curvature is different. So let's go back to 140, and we're gonna call that the high end of the permeability range. Okay. It's taking a little long. Well, let's say that permeability range is between 100 and 140 nanodarcies. and initial reservoir pressure can range between 26,420 and 26,570. So we've been able to identify a range of parameters. That's assuming we know the net pay, and we felt that the operator did very well with this test because we were able to get a fairly unique interpretation just after, in 100 nanodarcy rock just after 7 days of shut-in. Now getting to the end of today's presentation, so we're going to look at a few common questions that have come up in the past. Are there any real advantages to running a PITA over a mini-frac test? The answer is no, not really. The only real advantage to running a PITA over a mini-frac test is if fracking is not an option. Otherwise, PITA is just another test that we can use as an alternative depending on specific circumstances. What is the lowest permeability where PITA was successfully performed? As we saw in the previous example, PITA can be successfully performed in nanodarcy rock, although that requires additional planning and careful test design. What are the common mistakes when carrying out a PITA? Well, in majority of the data sets we see are dominated by wellbore storage, and we cannot determine reservoir characteristics uniquely. That's the biggest problem. It appears that operators are not taking test design seriously, whereas all the scenarios have to be examined carefully prior to running the test or even committing to the test. In summary, I can say that PITA is a suitable well test for tighter formations as a means to determine initial reservoir pressure and permeability. It's highly recommended for formation permeability of 0.1 millidarcy and higher. However, it can also be successfully carried out in lower permeability. Steps should be taken in that case to significantly reduce the wellbore volume, and the lower the permeability gets, the higher the risks of obtaining an unsuccessful test. So planning and careful consideration of all factors becomes extra important. This concludes today's presentation. Thank you for your attention. I hope you found this talk interesting and maybe you learned something new. If you have any questions, reach out to us. The contact information is on the very first slide.